Hello and welcome to Book Problems Chapter 5, Projectile Motion. Remember, there are actually three types of projectile motion. Only the first two are mentioned in the book problems. The third type, where it's a projectile launched from a raised platform at an angle greater than 0 degrees relative to the horizon. So make sure you have paper and pencil out, that you solve these problems before I finish discussing them to see if you have the same answer. Okay, the first question, first group, is going to be how does a vector quantity differ from a scalar quantity? Well, remember that a vector quantity is magnitude and direction, and the scalar quantity is just magnitude. For instance, mass, volume, length, while vector quantity is both magnitude and direction, such as speed and direction would be velocity. So only a vector quantity is specified by direction. Why is speed classified as scalar quantity and velocity classified as vector quantity? Speed is just the magnitude. Speed is the 40 kilometers per hour. Speed is simply the magnitude, while velocity is speed plus direction. For instance, northwest, that sort of thing, or some compass direction. If a vector that is 1 centimeter long represents a velocity of 10 kilometers per hour, what velocity does the vector 2 centimeters long drawn to the same scale represent? Well, scale is very important. So if it's 1 centimeter is 10, then 2 is 20. So the answer would be 20 kilometers per hour. When a rectangle is constructed in order to add perpendicular velocities, what part of the rectangle represents the resultant vector? Well, it would be the diagonal. The diagonal will be the resultant vector. We've done that many times from chapter 2. Will a vector at 45 degrees to the horizontal be larger or smaller than its horizontal and vertical component? By how much? Well, root 2. It's the 45 degree angle. The legs will be equal, and the legs will be 1, 1, and then the diagonal will be root 2. Kind of figure that out. You figure that out by yourself. That's very, very important. Or 1.41 times greater. So that finishes the first 5. Be careful to turn off the video, put it on pause while you're reading the next question before I can answer it, to see if you come up with the same answer. My answer may differ slightly from what the book says, but in addition to what the book says, it should be pretty complete. Why does a bowling ball move without acceleration when it rolls along a bowling alley? Well, there's no force on it. There's no friction. It's frictionless, so there's no force on it, so it's not accelerating. It's going at constant velocity. When something is, remember from chapter 2, moving at a constant velocity, there's no force on it. In the absence of air resistance, why does the horizontal component of velocity for a projectile remain constant while the vertical component changes? The vertical component is affected by gravity, where the vertical component does not have that. The horizontal components will certainly be affected by air resistance, but if we say that there is no air resistance, there's no force. Therefore, there's no force, there's no deceleration or acceleration, it's constant velocity. How does the downward component of the motion of a projectile compare with the motion of free fall? It's the same. The downward component is going to increase in terms of distance by 1/2 gt squared. by 1/2 gt squared. At the instant a ball is thrown horizontally over a level range. A ball held at the side of the first is released and drops to the ground. If air resistance is neglected, which ball strikes the ground first? They both fall at the same because the vertical component is governed again by d equals 1/2 gt squared. V naught t cancels because it's starting from rest. So they hit the ground at the same time. The next set of equations is coming up. After every set, there's going to be some time, so you can put it on pause and see if you can review the questions that have been answered. This is going to be a rather lengthy lecture. You may not want to watch it all at one time. So the next set, how far below an initial straight line path will a projectile fall in 1 second? Well, d equals 1/2 gt squared. So after 1 second, it will fall 1/2 of g is 5 times 1 squared would be 5 meters. Does your answer depend on the angle of launch or on the initial speed of the projectile? Defend your answer. No, the vertical drop doesn't, unless you're throwing it up, of course, and that would change things a little bit. But it's all governed again by d equals 1/2 gt squared. Neglecting air resistance, throw a ball straight up with a speed of 20 meters per second. How fast will it be moving when you catch it? It should be the same speed. It all should be going at 20 meters per second. It's going to be 20 meters per second up, and then it stops at the D max and then falls back down as 20 meters per second. 12A, neglecting air resistance. If you throw a baseball at 20 meters per second to your friend who is on first base, will the catching speed be greater than, equal to, or less than 20 meters per second? Well, the horizontal velocity will still be 20 meters per second. It will still be 20 meters per second. We're kind of getting ahead of ourselves here. Remember, that was number 12A. 11 came up. So just make sure that it's the same answer. Just make sure that you're keeping track of that. Does the speed change if air resistance is a factor? Yeah, the speed would be slower because of air resistance. That's a force. Force means acceleration, so it will be decelerating because you're applying that force to it. Next. What do we call a projectile that continually falls around the Earth? What do we call a projectile that continually falls around the Earth? Well, it's interesting to know that notice 12B is yes, it decreases. That's because of the air resistance. So what do we call a projectile that continually falls around the Earth? Well, it's interesting to note that the gravity on the space shuttle is not far below 9.8 meters per second squared. It's in an orbit. So an Earth satellite in orbit is continually falling. So if you're on the space shuttle, then if you're on the space shuttle and you are floating around, that's because you're in free fall. It's not because of zero gravity. That's a very, 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 very important distinction. The astronauts on the space shuttle are not experiencing 0G. They're just in free fall. Okay, the next one is we're going to rank each of the following sets of scenarios in order of the quantity or property involved. List them from left to right. If scenarios have equal ranking, then separate them with an equal sign. Okay, so we're going to rank the following scenarios. Hold on. Okay, 14 says the vectors represent initial velocities of projectiles launched at ground level. A, rank them by their vertical components of velocity from greatest to least. B, rank them from their horizontal components of velocity from greatest to least. Okay, now here we have the vectors. The best thing to do here would be to get out your calculators. The vertical vectors would be 10 sine 37, 20 sine 53, 10 sine 45, and 10 sine 30 degrees. You may also want to see if you can answer these more intuitively as well. And the answer is BCAD. Very easy problem to do if you have a calculator. Let's look at the horizontal components of velocity from greatest to least. Now remember, for the horizontal component, you need to go cosine the angle. So the first one would be to take the V0, 10 cosine 37, then 20 cosine 53, then 10 cosine 45, and then 10 cosine 30. Now remember that the vertical and horizontal component for C will be the same for both. And here we have BDAC. Now, if you reverse C and look at B is first in both and A is third in both, you might want to look at this differently relative to looking at them qualitatively. Okay, 15. A toy car rolls off tables at various heights at different speeds as shown. Rank them for the time in the air. Okay, so the one on the right will take the longest to go to ground, and then it would be 0.8 and then 0.6. So this is fairly straightforward. It would go CBA would be the distance, would be the time to ground. And then you take that time and multiply it by the velocity, and that is the answer to B. So rank them. So CBA, that's correct. Now multiply that by that value, time equals root d over 5, and that will give you t. Multiply that by the velocity, the Vx, and then you will be able to rank them relative to the distance they travel on the x-axis. So here you have root d over 5 equals t, and then t times 3, t times 3.2, and t times 4. Now remember, the t is going to be different in each one. So the largest t will be C and the smallest t will be A. And you get ACB as the answer. ACB as the answer to 15B. Again, you might want to look at it qualitatively. If not, the calculator will work just fine. Now, the next problem is going to be a little tricky. You're going to have to use your intuition to make sense of this. Water balloons of different masses are launched by slingshots at different launching velocities v. All have the same vertical component of the launching velocities. That's important. different V's, but same Vy. Ranked by the time in the air, from longest to shortest. Well, they're both going to have the same Vy. The four of them are going to have the same Vy. And so, it will be 2 seconds up, 2 seconds down. So A, B, C, D will be equal. A, B, C, D will be equal. All four of them will be in the air for 4 seconds. They'll all be there for 4 seconds. Now the next, so A, B, C, D, they're all equal. The next ranked by the maximum height reached from highest to lowest. Rank from highest to lowest, the maximum height. Well, how long is it going to take each one to reach the maximum height? Well, it'll be 2 seconds. So A will be 2 seconds, B will equal 2 seconds, C will equal 2 seconds, and D will equal 2 seconds. So what can you conclude, even though the Vx is going to be different in each of these? Notice that there's a mass given. Masses are completely irrelevant. Masses are irrelevant. So 2 seconds up, 2 seconds down, 2 seconds for all of them. So the height would be 2 seconds up. So it would be, if you dropped it from the height, it would fall for 2 seconds. So it would be 5d squared, or it would be 2 squared is 4 times 5 is 20 meters. They'll all be 20 meters. Now the next one says rank by maximum range. By maximum range. Well, the 45-degree angle would go farther, but be careful. Be careful. If you notice the Vx in B and D are actually going to be considerably larger. See, I'm sorry, in A and C will be considerably larger because they're both 20. So A and C, A equals C, but they'll be larger than B and D. So that's a little confusing. Look at it again and try to answer the question intuitively, and you'll see that even though the 45-degree, that's the rule, I understand, but look at it again. Very, very important problem to take care of. Now, here we have the plane, and it said in the previous slide you want to rank it from the greatest velocity to the least. So the wind that has the least effect on the forward motion would be the one with the greatest angle. So that would, the least angle, which would be D, and then B is a little bit more, and then A is even more, and then C is much more. So the greatest velocity would obviously be D, and the least velocity would be C. So it would be D, B. Even though D and B look equal, actually B is a little bit larger of an angle. So it would be D, B, A, C would be the answer. D, B, A, C, and that is correct. That is correct. Now, calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer per hour tailwind, and if it encounters a 50 kilometer per hour headwind. So you have a headwind and a tailwind. Remember what to do with that. The headwind you're going to subtract, and the tailwind you're going to add. So the tailwind will be 150 kilometers per hour, and the headwind will be 200 kilometers per hour. Okay, so that's the end of these problems. Let's take a quick break, and you'll never know I was gone. You'll never know I was gone. Calculate the magnitude of the resultant of a pair of 100 km/h velocity vectors that are at right angles to each other. So it would be the sum of the squares, and it would be 141 km/h. That would be the resultant. You're using the Pythagorean theorem. We're going to actually be using the Pythagorean theorem for the next few problems. So make sure that you know what that is, and that's going to be square root of a squared plus b squared. Calculate the resultant vector of an airplane with the airspeed of 120 km/h, pointing due north when it encounters a wind of 90 km/h, directed from the west. So they just want the airspeed, they don't want the direction. Even though the direction will be north of east, you might want to look at that, make sure it's coming from the west, it's heading east, so it's going to be north of east, and it's going to be 150 km/h is the answer to that. So you are taking the square root of the sum of the squares. Calculate the speed of raindrops hitting your face when they fall vertically, 3 meters per second, while you're running horizontally at 4 meters per second. Special triangle 3, 4, 5. So the answer is going to be 5. Make sure you draw that out, 3, 4, 5. You're going to see that quite a bit in physics. 3, 4, 5, that special triangle. Next, if you can do 21, you're going to be able to do 22, and you'll know that it's going to be 5 when they are at right angles. When 3 and 4 are at right angles to each other, the answer will be 5. So they'll add to magnitude of 5 when at right angles to each other. Okay, very straightforward. Number 23 is next. Pythagorean theorem, still doing that. But this one is a little bit different. Christopher can paddle a canoe in still water at 8 km/h. How successful will he be at canoeing upstream in a river that flows 8 km/h? Not very. His speed will be 0 relative to the land, so he's going to be working very hard to paddle the canoe. Not for a very fun day. Great for a workout, but that's about it. 24. How does the vertical distance of a projectile falls below an otherwise straight line path compare with the vertical distance it would fall from rest in the same time? In the same time, it would be the same. It would be the same. Next is 25. And we'll take a quick break, and you'll never know I was gone. I think we're going to do actually another set. The speed of falling rain is the same 10 meters above the ground as it is just before it hits the ground. What does this tell you about whether or not the rain encounters air resistance? No acceleration. Air resistance balances the weight of the raindrops, and the raindrops have reached terminal speed. They have reached terminal speed. 26 says, Marshall says that when a pair of vectors are at right angles to each other, the magnitude of the resultant is greater than the magnitude of either vector alone. Renee says he is speaking in generalities and that what he says isn't true. With whom do you agree? Agree with Marshall and cite how the diagonal of the rectangle has greater magnitude than either of its sides. How is the horizontal component of velocity for a projectile affected by the vertical component? Well, it is not affected. They are independent of one another. They are independent of one another. That's exactly what I said. Not at all. Horizontal and vertical components of velocity are independent of each other. Now, you're not going to want to watch this video all at once. It's going to be almost an hour. You're going to want to take a little bit at a time. If you pause it and begin it again, it's going to be considerably longer than an hour. So you want to take it a little chunk of time each time. Rain falling vertically will make vertical streaks on a car's side window. However, if the car is moving, the streaks are slanted. If the streaks from a vertical falling rain make 45-degree streaks, how fast is the car moving compared with the speed of the falling rain? How fast is the car moving compared with the speed of the falling rain? The car moves as fast horizontally as the raindrops fall vertically. Interesting concept, because the rain's falling vertically, the car is going horizontally, so those are the legs, and when the legs are equal, then you have 45 degrees. So 45-degree streaks, the car moves as fast horizontally as the raindrops fall vertically. An airplane encounters a wind that blows in a perpendicular direction to the direction its nose is pointing. Does the effect of the wind increase or decrease the speed across the ground? Or does it have no effect? Or does it have no effect on ground speed? An airplane encounters a wind that blows in a perpendicular direction. Well, the ground speed is increased in accord with the vector rules. Remember, if it's moving perpendicular, so those are the two legs, the movement of the airplane and the wind, so the diagonal will be longer than either leg, so the ground speed will be greater, and according to the vector rules relative to leg, diagonal. Okay. 30. A projectile is launched vertically at 50 meters per second. If air resistance can be neglected, at what speed will it return to its initial level? Where in its trajectory will it have minimum speed? Well, first let's take the minimum speed. That's going to be a d max, and then with all is equal, it's going to come back at the same speed. Okay, so it'll be minimum at the top, a d max, and it will have, remember, it's symmetrical, and you're not looking at any kind of maximum wind resistance or terminal velocity. It just goes, whatever goes up comes down. It's never going to work that way, but in the absence of air resistance, that's the case. Okay. A batted baseball follows a parabolic path on a day the sun is directly overhead. How does the speed of the ball's shadow across the field compare with the ball's horizontal component of velocity? Well, for the sun to be directly overhead, you have to be at the equator. That's first of all. But it would be the same. It would be the same. Because the shadow is moving at the same speed as the horizontal vector. And if you could actually see the horizontal vector, you'll see that it's the same. So the shadow and the horizontal vector are exactly the same. So let's take a break and then we'll come back. When air resistance acts on a projectile, does it affect the horizontal component of velocity, the vertical component of velocity, or both? Air resistance affects both vertical and horizontal velocities. It acts as a force, changing the velocity. It will decelerate anything in its way until that object reaches terminal velocity, and we'll talk about that in another time. Let's talk about it now. If I have something falling, it has a certain weight when it falls. It's not weightless, it still has a weight. However, there's no weight countering it. we call that the normal force. When you go on that, and that's your weight, there's a equal and opposite force pushing upward, and that's called the normal force. Let's get back to that. And pull into the passing lane without changing speed. Why does the distance increase between you and the car you're following? Something to consider. I'm not going to tell you. Let's go back. So the normal, when you're falling, you say you're weightless. That's in quotes. You're actually not weightless. You still have the same weight. The component along the direction of the road decreases, so the car ahead gains distance on you. That's pretty simple. So when you're falling and you have that weight, you have nothing against you, so you appear weightless, but you're actually, the normal is gone. But the air acts as a resistance, and when that resistance, Brandon launches a projectile at an angle of 75 degrees above the horizontal, which strikes the ground a certain distance down range. For what other angle of launch at the same speed would the projectile land just as far? So 75 degrees equals what? You can get that from the lecture. 45 is the longest. 30 and 60 is the same distance. And 15 and 75 are the same distance. Let's go back. So you're falling, right? And you're hitting all these air molecules. When you fall fast enough, you're going to hit a lot of air molecules. Pressure and force. Pressure is just force per unit area. So when you hit enough particles, you're going to have a force that's equal to your weight. And when that force is equal to your weight, you're no longer accelerating. There's no longer an unbalanced force. So you're going to stop accelerating and you're going to hit terminal velocity. It depends only on the vertical component of velocity as your feet leave the ground. Once off the ground, the only acceleration, neglecting the effects of air drag, is g, which is vertical. Your vertical liftoff velocity divided by g will be the time that you move upward. Double this and you have your hang time. I don't think there's a question here, actually. When you jump up, your hang time is the time your feet are off the ground of velocity when you jump. Your horizontal component of velocity, or both. Defend your answer. This is for the question. Interesting. So when you're reading the answer, what is it that you're reading? Interesting. The hang time of a basketball player who jumps a vertical is 2/3 seconds. What will be the hang time if the player reaches the same height while jumping a horizontal distance of 4 feet, 1.2 meters? Kind of like Michael Jordan when he starts at the key. He appears to be floating in the air. Does that horizontal velocity when he leaps towards the basket, does that increase his hang time? That's really the question here. Since in this case, the height is the same, either way, hang time is the same either way. So the hang time is independent of the horizontal velocity. We said before, the horizontal velocity and the vertical velocity are independent, unique quantities that can be combined to form the parabolic shape. But in terms of mathematics, they can be distinct and worked on individually. Sneasley flies at a speed of 10 meters per second in still air. If he flies into a 2 meters per second headwind, how fast will he be traveling relative to the ground? So it would be 10 meters per second, and then what would you do with the 2 meters per second? It's a headwind. So what are you going to do to the 2 meters per second? Well, you're going to subtract the 2, and you're going to end up with 8 meters per second because it was a headwind. Headwind subtract, tailwind you add. Let's go back to terminal velocity. So you jump out of an airplane and you're accelerating because you have this force of your weight. That's an unbalanced force because you don't have the normal. When you hit enough air, it's going to equal your weight, and that's going to be your terminal velocity. That's actually what happens. Relative to the ground below, how fast will he travel when he experiences a tailwind of 2 meters per second? I think I already answered that. 10 meters per second plus 2 meters per second is 12 meters per second. Let's go back again to the terminal velocity. Terminal velocity, people think it's going to hit your head and go through your head. Well, in fact, it reaches a horizontal, terminal velocity very, very quickly. So you don't really have to worry about it. It's certainly going to stick. The penny is light, so it's going to reach a terminal velocity very quickly because it's light and it's going to hit a equal resistance to its weight. Okay, while flying at 10 meters per second, suppose that he encounters a 10 meters per second crosswind coming at right angles to his heading. What is the speed relative to the ground? So it's 10 one way, 10 the other way. So the diagonal will be, the resultant will be root 2. You remember that? 1 root 2 is special triangle, 45 degrees angles. So 10 times root 2 is going to be 14.1. 14.1. The legs are equal, therefore the direction is 45 degrees. I don't know where I got north of west, but either way, if he was going north and the wind was coming from east to west, then it would be 45 degrees north of west. I hope you can picture that. So you're flying north, it's coming out of the east, heading west, so it's going to knock you into the north of west region. Okay, a boat is rowed at 8 kilometers per hour directly across a river that flows at 6 kilometers per hour as shown in the figure. What is the resultant speed of the boat? A boat is rowed 8 kilometers per hour directly across a river that flows at 6 kilometers per hour as shown in the figure. What is the resultant speed of the boat? We're going to take a quick break. You'll never know I was gone, and we'll get back in a moment. And you can plainly see that the legs of the triangle are going to be 8 and 6, and the hypotenuse will be the square root of the sum, 64 plus 36, the squares of the legs. And you can also see that it's clearly a 3, 4, 5 triangle, special triangle. So the answer would be 10, because it's going to be 2 times 5, because it's 2 times 4 is 8, and 2 times 3 is 6. So it'll be, instead of 3, 4, 5, it'll be 6, 8, 10. So that's a pretty straightforward problem to do. Now, what if I wanted to go directly across the river from the beach or the shore that I was on and go directly across? How fast and in what direction can the boat be rowed to reach a destination directly across the river? Well, think of the right triangle that was used to solve it, of which 8 and 6 were legs and 10 was the hypotenuse, as part of an isosceles triangle where there's symmetry. This was the drawing that was used to help solve the problem. Now, what happens if I wanted to go directly across? Well, I would say the river's going 6, I want to go 10, and what would be the other leg? It would be 8. And what would the angle be? Well, as you can see from this drawing, theta is 53. That would be relative to the original bank. Beta is the angle relative to the direction you want to go, you want to end up going. So the answer is going to be 10 kilometers per hour at a distance of 37 degrees upstream from the original direction, or 53 degrees relative to the original bank. So the speed is the same, but the direction is different. So the angle is actually going to be the same, but then you have to say where that angle is, or draw a picture. The best way to do it is to know your compass directions when you're solving these problems. If a 14 unit direction makes an angle of 45 degrees with the horizontal, what are its horizontal and vertical components? Well, first of all, the components would be the same because it's 45 degrees. You remember the special triangle from geometry, 45 degrees, it's 1 root 2. So if it's 14, what would be, 14 would be root 2 of what number? And, or you could just simply say cosine 45 degrees equals adjacent over 14 would be 10 units. Understand this, that the opposite, the other leg, would also be 10 units. So you could think of it in terms of a special triangle, 1 root 2, and what number is root 2 14 of. So the next one, it says Harry accidentally falls out of a helicopter that is traveling at 15 meters per second. He plunges into a swimming pool 2 seconds later. Assuming no air resistance, what was the horizontal distance between Harry and the swimming pool when he fell from the helicopter? Well, thank God there was a swimming pool. But he's falling from rest. So he's falling from rest, and he's falling 15 meters horizontally. Okay, and he plunges into a swimming pool 2 seconds later. So what was the horizontal distance? Well, we're not concerned about the vertical distance, but the horizontal distance would be the horizontal velocity, which doesn't change, is times 2 seconds, which is 30 meters. Okay. Assuming no air resistance, what was the horizontal distance between Harry and the swimming pool? Okay, so it's going to be 30 meters even. Well, if you refer back to the original problem, 40, what are the horizontal and vertical components? Harry's velocity just as he hits the water. Well, what would be the horizontal? The horizontal component would be the easiest. What do you think the horizontal component would be just as he hits the water? Well, the horizontal component remains constant, 15 meters per second, and that's what it always is. The vertical component is a little different. Remember, he's falling from rest, so you can use the shortened equation Vy equals Gty, which is going to be 10 meters squared, it's positive, times 2 seconds, and that's 20 meters per second. Now, show that Harry hits the water at a speed of 25 meters per second. Well, 3 times 5 is 15, and 4 times 5 is 20, and 5 times 5 is 25. So it's going to be actually a 3, 4, 5 triangle. So if you take the square root of the sums of 20 squared plus 15 squared, you'll see that it's 25 meters per second. Or you could just simply cite the 3, 4, 5 triangle. So he's going to hit his resultant velocity when he actually hits the water will be going down at 25 meters per second. You will have to show that at several places with type 1 and also type 3 horizontal motion. Harry and Angela look from their balcony to a swimming pool below that is 15 meters from the bottom of their building. They estimate the balcony is 45 meters high and wonder how fast they would have to jump horizontally to succeed in reaching the pool. What is your what is your answer? Do not try this yourself. Do not try this yourself. Well, the time to reach is 3 seconds. So they're 45 meters high. It would take 3 seconds, and to cover the 15 meters, they would have to be going 5 meters per second. It might be instructive to determine, well, what does that mean in terms of miles per hour? How fast are you going to have to actually be running? 5 meters per second is actually pretty fast. A girl throws a slingshot pellet directly at a target that is far enough away to take 0.5 seconds to reach. How far below the target does the pellet hit? How high above the target should she aim? So it's going to fall. The target is far enough away to take 0.5 seconds to reach. So it's going to be 1.5. She's got to aim 1.25 meters above the target. She's got to aim 1.25 meters above the target. What would that mean in terms of how long it's actually going to take to get there? Well, it would be 0.5 seconds to get there, and you're starting from rest. Next, the boy on the tower in the figure below throws a ball a distance of 60 meters as shown. At what speed in meters per second is the ball thrown? At what speed is the ball thrown? Well, first of all, how high is the tower? It's 20 meters. How long would it take the ball to fall? And then what about the 60 meters? It would be 60 meters divided by the time. So it takes 2 seconds to fall, and then 60 meters divided by 2 seconds, which is 30 meters per second, which would be 30 meters per second. So the two velocities are independent, the x and the y. The y is starting from rest, it's falling down, and it's going to go at, and also tx equals ty. A cannonball launched with an initial velocity of 141 meters per second at an angle of 41 degrees follows a parabolic path and hits a balloon at the top of its trajectory. Neglecting air resistance, how fast is it going when it hits the balloon? What is the acceleration of the cannonball just before it hits the balloon? Just before it hits the balloon. Well, if it's going 140 meters per second at an angle of 45 degrees, you know that it's going 100 meters per second because of root 2, the root 2. What's root 2 of 141? Or you could apply the basic trigonometric functions. So the acceleration remains constant. That's number one. The acceleration remains constant. What is the acceleration of the cannonball just before it hits the balloon? The acceleration is always 10 meters per second squared. It's negative going up and positive going down. Contrary to what a lot of physics books say, we use in our class negative 10 going up and positive 10 coming down. So both the vertical and the horizontal components are equal because of the angle 45 degrees. Vx equals Vy equals 100 meters per second. The horizontal velocity is 100 meters per second, and the vertical velocity is 0, okay, at the top. Okay, the acceleration due to gravity is always 10 meters per second. That's what the word constant means. So the vertical velocity is 0 just before it reaches d max. Joshua throws a stone horizontally from a cliff at a speed of 20 meters per second, which strikes the ground 2 seconds later. Use your knowledge of vectors and show that the stone strikes the ground at a speed of 28 meters per second. So he's going to throw the stone vertically at 20 meters per second. So that will remain constant. 2 seconds later, so that means that it's going 20 meters per second in the y direction and 20 meters per second in the x direction. So if you use the Pythagorean theorem, what is 400 plus 400? Square root of 800, and that's going to be the answer to the question, because 20 squared is 400 and 20 squared is 400. That's 800. So what's root 800? And so that's going to be, the yellow is going to be the resultant vector in hitting the ground. That will be the resultant vector. So if that's the resultant vector, is it clear to you that the hypotenuse would be the square root of the sum 20 squared plus 20 squared? And that would be the answer to the question. So that would be 28 meters per second. And at what angle does it strike the ground? 45. Why 45? Because each leg is 20 meters per second and 20 meters per second and 20 meters per second. So that would be the arctangent of 20 over 20 is 1, which is 45 degrees. 45 degrees. Again, you're going to have to know how to do that problem. Calculate Hotshot Harry's hang time if he moves horizontally 3 meters during a 1.25 meter high jump. What is his hang time if he moves 6 meters horizontally during his jump? During his jump. So he's going horizontally 3 meters during the jump, or 6 meters during the jump. Well, I'll tell you right now, the horizontal motion is utterly and absolutely, positively, 100%, without a doubt, irrelevant. So it's going to go 0.5 seconds up, 0.5 seconds down, and his hang time will be 1 second, which is approximately the world record for jumping. Okay, which is probably the world record for jumping vertically. Okay, Megan rolls a ball across a lab bench, dy meters high, and the ball rolls off the edge of the bench with horizontal speed vx. From the equation dy equals 1/2 g ty squared, which gives the vertical distance dy, an object falls for rest. Derive an equation that shows the time t taken for the ball to reach the ground. Okay, so it's going to be from rest, it's going to be ty equals root 2 dy over g, which should be quite routine for you now after doing chapter 4, which should be routine after doing chapter 4. Let's take a break. You'll never know I was gone. Be right back. Okay, we are actually on the last problem. We have 2 more parts to it. The next is write an equation showing how far the ball will land from a point on the floor directly below the edge of the bench. Understand that the horizontal speed Vx doesn't change, that the time to drop the Tx, the Ty equals the Tx. So therefore, dx equals Vx Tx, which equals Vx Ty, which equals Vx root 2 dy over g, or simply Vx dy over 5, root dy over 5. So now what we'll do is we will use that equation. We'll calculate the time in the air and the landing location for Vx equals 1.5 meters per second and the bench height of 1.2 meters. Calculate the time in the air and the landing location for that speed and that height. So it will be dx equals Vx root 2 dy over g, which equals 0.74 meters. It's going to land 0.74 meters away from the edge of the bench.